ThyssenKrupp steel produces flat steel by sintering iron ore, coking coal, smelting in blast furnaces, refining pig iron into steel, and continuously casting it into slabs for rolling. Skilled operators carefully monitor the forging operation, controlling the movement and positioning of the hot metal to shape components like shafts, blocks, rings, or custom parts. This open die process is particularly suited for large, custom-shaped forgings, such as hydroturbine shafts, hollow tubes, gear rings, and windmill components. After forging, the workpieces are cooled in a controlled manner to prevent internal stresses or cracks. Depending on the final requirements, the forged components may undergo heat treatment, rough machining, or further finishing processes to achieve required tolerances and properties. This open die forging method allows Alka to produce strong, durable, and precise components with excellent structural integrity, suitable for demanding industrial applications. The forging process at Alka begins with the selection of high-quality raw materials, which are cut into required lengths based on product specifications. These billets or ingots are then heated in a furnace to a temperature suitable for plastic deformation, usually between 1,100 degrees Celsius to 1,250 degrees Celsius, depending on the type of steel used. Once heated, the metal is transferred to an open die forging press and power hammer. In this process, the material is placed between two flat dies that do not contain any specific shape impressions. The metal is then deformed by applying successive compressive forces through repeated hammer blows or controlled pressing actions. Since the dies are open, the metal can freely expand laterally, and the forging team must continuously manipulate and rotate the workpiece to achieve the desired geometry. Milled with binder, dried into granules, pressed under 12-ton force, sintered at 1,500 degrees Celsius, ground precisely, PVD. The manufacturing process of super bearings begins with the careful selection of premium raw materials. Chrome steel 52,100, stainless steel, and specialized alloy steels are used due to their superior wear resistance, fatigue strength, and hardness. These materials are chosen to ensure that the bearings perform optimally in high-load and high-speed applications. Once the material is selected, steel bars are cut into smaller cylindrical pieces called blanks. These blanks are the starting point for the inner and outer rings of the bearing. Depending on the bearing design, the blanks undergo either forging. Forging reshapes the blanks under high temperature and pressure, improving the internal structure and strength of the material. After the initial shaping, the components are further refined through turning and grinding. Turning machines remove excess material from the blanks, refining their shapes and ensuring precise concentricity. Grinding is then performed using abrasive wheels to achieve high dimensional accuracy and fine surface finishes, which are critical for the smooth operation of the bearings. Once the components are machined, they undergo heat treatment. Heat treatment processes, including hardening, tempering, and annealing, enhance the material's hardness, strength, and fatigue resistance. These processes alter the internal structure of the steel to ensure the bearings can withstand high-stress conditions. The components are carefully cooled in a controlled environment to prevent distortion and ensure the desired properties are maintained. After heat treatment, the components are washed thoroughly to remove any contaminants, such as oils or metal particles, left from previous processes. Cleanliness is essential for the next assembly phase. In the assembly stage, rolling elements such as balls or rollers are inserted between the inner and outer rings. A cage or retainer is used to maintain uniform spacing between the rolling elements. Seals or shields are also added if needed to protect the bearing from contamination. Finally, the bearings are lubricated with premium oils or greases to reduce friction, dissipate heat, and prevent corrosion. Each bearing undergoes rigorous testing and inspection before being packaged for shipment. The helical interpolation process on the Fermat WFT13 CNC bed milling machine uses the UHA Michigan 30 micro-indexing head with 30 kilowatts power, 1,600 nanometers, and micro-indexing precision of 0.001 degrees/0.001 degrees. The process involves operations such as drilling with a carbide insert, drilling with a carbide drill, tapping M16, M24, and chamfering 45 degrees. The machine is equipped with a robotic tool changer capable of handling heavy tools up to 75 kilograms, ensuring continuous operation without interruption. At Klingenberg's factory in Huckeswagen, Germany, the bevel gear production process starts with selecting high-quality raw materials. Gear cutting is carried out on the world's largest face-hobbing C300 machine. The gears are then ground using an economical grinding process for sizes up to 1,100 millimeters, with burn detection applied to all ground bevel gears. Heat treatment is performed with a capacity of 140 tons per month. CNC technology is used for all turning and grinding operations, while the tool setup is fully automated based on Klingenberg's CMOS calculation. The process includes integrated manufacturing with a reliable closed-loop concept and continuous quality checks. The ITER vacuum vessel manufacturing process involves several steps for each segment. The inboard segment includes inner shell forming, FSH hole machining, E-beam welding, IWS rib welding, and outer shell welding. The upper segment requires FSH hole machining, intermodular key welding, PAUT testing, and final machining. The equatorial segment involves inner shell fabrication, FSH welding, IWS rib welding, and outer shell welding. The lower segment includes E-beam welding, shell machining, TRS installation, and helium leak testing. The aluminum extrusion process begins with billet cutting, where the aluminum billets are preheated in a furnace to a specific temperature for optimal extrusion. The billets are then transferred to a mold preheating furnace, followed by extrusion through a 6000 T. The extruded shapes are then heat-treated in a 13.5-meter aging furnace to enhance strength and durability. Afterward, they undergo straightening with a multi-axle straightening machine to ensure size precision. Cutting is performed using a 45 degrees double-blade angular saw for precise angular cuts, followed by an electric automatic cutting machine for accurate length and surface flattening. Finally, quality control is carried out using advanced instruments like Webster and Barkol hardness testers, 3D measuring machines, and flatness measuring instruments to ensure product precision. At Liberty Steel Dalzell, steel plate production begins with heating steel slabs to approximately 985 degrees Celsius. These slabs are then rolled using a reversing plate mill, reducing thickness from about 290 millimeters to as thin as 15 millimeters. This rolling process refines the grain structure, eliminates internal porosity, and enhances mechanical properties. Depending on customer requirements, the plates may undergo further treatments such as normalizing, tempering, or thermomechanical controlled processing. The mill can produce plates up to 150 millimeters thick, 20 meters long, and 3.95 meters wide. After rolling and heat treatment, the plates are tested for strength, toughness, and chemical composition to ensure compliance with construction and structural standards. Thick steel plates are rolled using the Faxon HAV 240, a powerful 3-roll plate roller with variable geometry. With a maximum rolling thickness of 240 millimeters and plate width up to 4,200 millimeters, it ensures extreme precision. The plate is positioned on the feeding table and clamped securely. The CNC system controls the roll movement precisely, adjusting the lower rolls for optimal pre-bending. As the plate passes through, it is gradually shaped into cylindrical or conical forms with tight roundness tolerances. iBend, a laser-based system, provides real-time radius correction, automatic calibration, micro-positioning, and an electronic balancing system guarantee perfect repeatability. Fully automated support stabilizes the plate during rolling, ideal for manufacturing monopiles, transition pieces, jackets, and tripods. The stamping process for manufacturing Lada car body components begins with receiving high-quality sheet metal, compliant with Russian and European standards. Coils of steel are unrolled, leveled, and cut into blanks. These blanks serve as the starting material for stamping operations. The blanks are transferred to press lines, which consist of mechanical and hydraulic presses with capacities ranging from 100 to 2,000 tons. Depending on the part, the process may involve several stages such as blanking, trimming, bending, piercing, and deep drawing. Deep drawing is especially important for forming exterior panels like doors, roofs, and hoods, requiring high tonnage and precise control. Each stamping line is equipped with automated feeding systems and robotic arms to transfer parts between stations. The dies used in each press are carefully aligned and maintained to ensure consistency and surface quality. In-process inspections are carried out at various points to check for defects, deformations, and dimensional accuracy. Damaged or worn dies are repaired and maintained in-house using metal cutting and machining equipment. This large-scale operation processes around 600 tons of metal monthly. Once stamped, the parts are sorted and transferred to the next stage of body assembly or delivered to automotive manufacturers as high-precision components ready for welding and painting. Sany Group operates a wide range of advanced manufacturing facilities across China, each specializing in different heavy equipment products. These include the drilling rig, medium excavator factory, mini excavator factory, and large excavator factory, which focus on earth-moving and excavation machinery. The STE slewing bearing produces high-precision components for rotational systems. The Huawei factory and the Zhongxing factory support various stages of equipment production, while the factory of concrete machinery specializes in concrete pumps and mixers. For infrastructure development, the Huayuan factory manufactures advanced road machinery, SANY also operates factories for large and medium tonnage mobile cranes and an off-highway mining truck factory for mining and transportation sectors. The factory of hydraulic support produces underground mining supports, and the blade factory in Zhangjiakou specializes in large blades for wind energy or construction. Additionally, the factory of secondary manufacturing provides key structural parts, enhancing the group's integrated supply chain. Welded truck bodies from the body shop are first cleaned, rinsed, and immersed in a zirconium pre-treatment bath to clean and etch the metal surface. After a second rinse, an electrodeposition e-coat primer is applied using a cathodic process to prevent rust and corrosion. The e-coated bodies are then baked in an oven to ensure complete coverage and durability. Following a manual inspection, robotic sealing operations are performed to make all seams watertight, and liquid-applied sound deadener is added for a quieter ride. After a second inspection, the truck bodies move to the anti-chip cell, where robots spray a protective coating on lower sides, rockers, and fenders. Before priming, ionized feather dusters remove any remaining dust. A solvent-borne primer is applied robotically, then cured in a split oven. After another surface inspection and preparation, the truck bodies are dusted again and sent to one of 10 paint modules. Robots precisely apply the base color and a clear coat. After a final bake, inspectors at the finesse deck ensure the finish is flawless before the trucks move to general assembly. The production of a Toyota car follows 5 major stages: stamping, welding, painting, assembly, and inspection. It begins with large steel plates, which are cut, punched, and pressed into shape under 1,600 tons of pressure. These shaped parts, such as doors and hoods, form the car's body foundation. During welding, the floor, sides, and roof are assembled with high precision, connecting as many as 4,000 welded points. Additional parts like the doors and trunk lid are also attached. After welding, the body undergoes a washing process before entering the painting stage, which includes priming with rust-resistant paint, sealing joints, applying a middle coat, color painting, and finishing with a clear coat for shine and protection. Once dried, the car proceeds to assembly, where over 3,000 parts including electrical wiring, the engine, brakes, tires, and windows are installed along a production line over half a mile long. Finally, inspectors thoroughly check the assembled vehicle for correct part installation, surface quality, mechanical functions, and leaks. Only fully approved cars are shipped to customers worldwide. The production process of Bohai steel drums begins with the preparation of steel sheets, which are cut into circular shapes. These discs are then formed into cylindrical bodies through a deep drawing process. The edges are welded to form a seamless structure. Afterward, the drum's body undergoes a rolling process to smooth the surface. The lid is also formed and welded to the body. Finally, The drums are subjected to a coating process for corrosion resistance, followed by quality inspection before being packed for shipment. The aluminum rolling process at JW begins with melting a mixture of scrap and prime aluminum in furnaces. The molten metal is cast into coils, then reduced in thickness using a coal mill. After annealing to soften the metal, further reduction occurs in the foil mill. The coils are then slit to desired widths, lubricated and tested. Finally, the coils are packed and shipped to customers. The 13,000-ton large open die forging press operates by shaping massive metal billets under extreme pressure. First, a heated billet is positioned between the press's upper and lower dies. The press then applies a vertical force of up to 13,000 tons, compressing the billet and altering its shape. The workpiece is frequently rotated and repositioned between presses to achieve the desired dimensions and internal structure. Operators may perform multiple forging strokes, gradually refining the billet. This process improves the material's strength and eliminates internal defects. Throughout the operation, precise control, position, and temperature ensure superior forgings for critical applications such as aerospace, energy, and heavy machinery components. The 13,000-ton large open die forging press operates by shaping massive metal billets under extreme pressure. First, a heated billet is positioned between the press's upper and lower dies. The press then applies a vertical force of up to 13,000 tons, compressing the billet and altering its shape. The workpiece is frequently rotated and repositioned between presses to achieve the desired dimensions and internal structure. Operators may perform multiple forging strokes, gradually refining the billet. This process improves the material's strength and eliminates internal defects. Throughout the operation, precise control, position, and temperature ensure superior forgings for critical applications such as aerospace, energy, and heavy machinery components. At MAN Prime Serve Hamburg, advanced technologies are employed for marine engine service and maintenance. The center uses laser welding for precision repairs and custom-made pipe connections, such as cooling pipes. Tools are designed to reduce crankshaft damage, and piston crack testing ensures high-quality reconditioning. The welding of piston crowns is performed to restore engine parts to optimal condition. These processes, combined with modern machinery, minimize carbon dioxide emissions and reduce customer costs, ensuring reliable. The production of 15 TCG 2032 V16 gensets for Precision Energy in Bangladesh took place at MWM's Mannheim facility, Germany. The process included comprehensive planning and manufacturing within a 3-month time frame. The gensets were rigorously tested for quality before delivery, ensuring reliable energy solutions for the customer. In Vicksburg, Mississippi, a massive oil platform takes shape at the shipyard. The hull, a robust triangular base, supports 3 legs that anchor into the ocean floor. Powerful engines raise the platform above the highest waves. In Vicksburg, Mississippi, a massive oil platform takes shape at the shipyard. The drilling tower is then installed, and workers begin boring deep into the seabed. Designed for the Gulf of Mexico, the Tarzan-class platform drills over 11 kilometers, enduring harsh conditions. Once complete, it's towed 600 kilometers to tap vast oil reserves. Hyundai Heavy Industries' shipbuilding process involves assembling numerous blocks to create large ships. The company utilizes advanced facilities, including automatic welding robots and CNC cutting machines. Synergy across divisions like engine and machinery and electro-electric systems ensures innovation, while a strict quality management system guarantees top-quality vessels. The production process of railway wheels at the rail wheel plant in Bella involves several key steps. First, molten steel is poured into graphite molds using bottom pressure pouring technology. Once the metal solidifies, the cast wheels are removed and undergo a series of machining operations, including turning and boring, to achieve the desired shape and dimensions. After machining, the wheels are subjected to rigorous quality control tests in the plant's NABL-certified lab, which checks chemical composition and metallurgical properties. Finally, the wheels are inspected for defects, heat-treated for strength, and tested for durability before being packaged and sent to customers. The cleaning and rebuilding process for the Komatsu PC450 hydraulic pump at CJ plant is a precise, multi-step procedure designed to meet OEM specifications. Upon arrival at the workshop, the pump undergoes an initial thorough cleaning to remove accumulated dirt, grease, and hydraulic fluid residues. This ensures a clean surface for accurate inspection and prepares the unit for disassembly. Skilled engineers then carefully dismantle the pump, meticulously examining each component for signs of wear, damage, or fatigue to determine the scope of repairs needed. During the repair phase, all identified worn or damaged parts are replaced with genuine Komatsu components to guarantee long-term reliability and performance. Essential elements, such as bearings, seals, and O-rings, are automatically renewed to maintain the pump's integrity and prevent future failures. Mating surfaces are precision reworked to ensure perfect alignment and seamless operation. To eliminate any remaining contaminants, the pump is cleaned again thoroughly before the reassembly process begins, ensuring no debris compromises the rebuild. Reassembly is carried out with utmost care, with engineers methodically fitting each component to exact OEM standards. All fittings are cleaned, and new O-rings are installed to ensure leak-free performance. Once fully reassembled, the pump is subjected to comprehensive testing on a custom-built test rig, specifically designed to simulate real-world operating conditions. This rigorous testing verifies the pump's functionality, pressure capacity, and overall performance. The fully reconditioned Komatsu PC450 hydraulic pump, restored to peak condition, is then prepared for shipment, complete with a 12-month warranty. This meticulous process reflects CJ Plant's dedication to delivering high-quality, reliable hydraulic solutions for their customers worldwide.